All right. Good morning, everybody. Um, Hopefully you had a chance to watch the video yesterday. Let me go ahead and let me start the timer here so I keep myself on track. Um, Hopefully you had a chance to watch the video yesterday and kind of was able to kind of wrap up and summarize and in your own way summarize your understanding of what Ka and Kb are and be able to incorporate that into the discussion of polyprotic acids. Then we started our discussion of salts, and remember, salts are ionic compounds, and so how ionic compounds then could also possibly affect the pH of a solution. Okay, and that is, we're basically discussing acidic and basic properties of compounds that are not acids nor bases. And so we started that discussion yesterday, and hopefully you're able to kind of wrap your mind around our discussion of the first type of ionic compound. And we saw then ionic compounds that make neutral solutions. Okay, and so I kind of want to pick up with that really quickly. And then please make sure then, like I said, you come by and ask your questions about this here, because it is important that you understand how ionic compounds, what we refer to as salts, will also affect the pH of water. Okay, so remember here, and let me go ahead and share my screen here with you, and then we'll get started with it. Okay. All right, so we have water here. Let's just make sure we understand. Water is neutral, regardless well, for the most part, what type of water it is, whether it's bottled water or water from the tap. We know then that water here is essentially neutral, which means then when we take when we measure the pH of water, okay, the pH of water is going to be right around 7. Okay, right around neutral, depending on again what type of water you have. It's going to be right around 7. Okay, which means then the hydrogen ion concentration in the water, okay, it's going to be roughly about 1 times 10 to the minus 7 molar. So that's what we know about neutral water, which means then the hydroxide ion concentration, if we use the Kw, the ion dissociation constant for water, we would get those concentrations as well. So therefore then, concentrations of hydrogen ions, hydroxide ions are right at the right around 10 to the minus 7, which is not that much at all. And this is based upon the dissociation that we learned about, in which water then dissociates into the hydrogen ions and the hydroxide. So this is the process by which we were examining. Okay. Now, if we add to this then, and we saw this, if we and we were talking about this yesterday, if we add to this a ionic compound such as sodium chloride, for example, or if we add to the compound, add to the water a compound like sodium hydroxide or calcium chloride. Okay. So if we add, these are all ionic compounds. We refer to these as salts, okay, because the definition of a salt then, and not the common term for salt. The common term for salt is just referring to sodium chloride. Okay? But if salts then are just ionic compounds that can dissolve in water. Okay, in water. Okay. And so if we add one of these salts into the water itself, okay, we know then what happens is that they dissociate. They break up into their ions, with sodium chloride becoming sodium ions and chloride ions, with sodium hydroxide becoming sodium ions and the hydroxide ion, and with calcium chloride being then calcium 2 plus and 2 chloride ions. Okay, so that's what we know happens. Okay? So what we need to take a look at then is there a process by which these ions interact with the water? And if there is, okay, where would the equilibrium lie? Okay, so let's go ahead and let's take a look at what happens then. Let's imagine then that sodium ion, okay, it's going to interact with the water when it's in there, okay? And let's say for right now, that's equilibrium. We will get then a situation in which you have the water now behaving as a this is your conjugate acid for the sodium chloride for sodium hydroxide here. Okay, and so with that said, then it will interact with the water to form sodium hydroxide and a hydrogen ion. Okay, now, folks, we need to make sure we remember that this process then will not happen. Okay, now if it did, now let's imagine if it did, we're generating hydrogen ions right here. So if this process, this first process here does happen where sodium interacts with water, okay, we're going to form hydrogen ions. And if that's the case, then the pH is going to go way down. It's going to be less than 7. Okay, so if this happens, if the sodium ions here interact with water to form hydrogen ions, we have then an acidic solution. Okay, so we have then an acid. If that's the case, we don't see that happening. Sodium ions do not do that, and so what we see happening here is that this process does not happen at all. The second reason why we know this doesn't happen is because you're forming a very strong base here. Sodium hydroxide is a very strong base, and we know then that the sodium hydroxide, okay, whenever you add that to water, the equilibrium lies far, far to the right, which means that even if this process does happen, as soon as sodium hydroxide forms, we shoot right back to the left-hand side, so that if this process did happen, equilibrium will lie very far to the right with almost nothing happening on the right-hand side, nothing forming on the right-hand side. Okay, so that's what the sodium ion is. So the sodium ion then is, if you want to think about it, the sodium ion is going to be then the conjugate acid of a strong base. So whenever you have a conjugate acid for a strong base, such as sodium hydroxide, the pH, it will not change to pH water because this will not happen. Okay? So if that doesn't happen, we don't have this happening at all. Okay, so for the conjugate acid of a strong base, like the sodium ion here, conjugate acid of a strong base, we're going to see then that it will not change the pH of water. The pH of water will not be affected by a conjugate acid of a strong base. Okay. All right, let's take a look at another possibility, possible occurrence here, and that is the chloride ions. Okay. So let's go ahead then, let's take a look at the conjugate base here of a very strong acid. We'll talk about this in just a moment. And the reason why this is the conjugate base of a very strong acid is because if we took hydrochloric acid, okay, and we dissolved it in water, we get then the hydrogen ions and the chloride ions. Okay, so this is the conjugate base of a very strong acid. So let's see what happens then when we take the conjugate base of a very strong acid like chloride and react it with water. Okay, and let's see if something happens. Okay, if this does happen, then here water is going to serve as a base. Okay, I'm sorry, this is going to serve as an acid. Okay, and it's going to donate the hydrogen ion to the chloride. You form then the hydrochloric acid and the hydroxide ion here. Okay, so if this did happen, you'd form hydroxide ions right there, which would send the pH, make it more basic, way above 7. Okay, and this then would be a base solution. Okay? That's if this happened. However, let's imagine what we have here, and I'll point this out up here as well. Okay, what we have here then is we form then a very strong acid. So we form a very strong acid, and we already said then with a very strong acid like hydrochloric acid, the equilibrium shifts back towards the left almost completely. Okay? So again, just like up here, as soon as the hydrochloric acid forms, it's going to shoot right back. That means it's going to dissolve and set it back in this direction here. And so that means that very much like this does not happen, this process doesn't happen either. Okay, that doesn't happen either because, like I said, you're forming a very strong acid here, and you're forming a very strong base here. Okay? And the other thing that I failed to mention that understand this: the hydrogen ion, if it does form here, it's going to react right away with the sodium hydroxide to get back over here. Same thing here: the hydroxide ion is going to react right away with this strong acid here and send it back towards the left. And because of those two, for those two reasons, this will not happen, so that you will not get, when you add the conjugate acid, a conjugate base for a strong acid. So whenever you add a conjugate base of a strong acid, it will not change the pH of water. So you still get a pH of 7 because this process doesn't happen. That means then the chloride ions, the sodium ions, they don't do anything because they don't interact with water. And that's going to be important because when we start talking about weak acids, the conjugate bases and conjugate acids of weak acids, that's a different story. Okay? So here then we are dealing with strong bases, conjugate bases, and conjugate acids of strong bases and strong acids respectively. Okay, so you got to keep that in mind. And this is another reason why you got to make sure that you memorize the different strong acids and the different strong bases. Okay, all right. So that's what we saw. So whenever you have a salt, whenever you have an ionic compound that is made up of either the conjugate acid of a strong base, or the conjugate base of a strong acid, if one of the ions is derived, can possibly be derived from a strong base, a strong acid, that ion does nothing to the pH of the water itself. Okay. All right. Let's go ahead then, and let's consider then the case that I just told you. Let's consider then what happens if you take, let's say, let's do your acetic acid. Okay, so let's take acetic acid. Okay. So this is acetic acid right here. This is the formula for acetic acid. Okay. And so let's consider what happens when you take acetic acid and you add it into water. Okay. So this is now acetic acid is a, so this is acetic acid. Let me write this here. This is acetic acid. Okay. So let's take a look at acetic acid. So acetic acid then has this, and let's go ahead and let's see what happens if you add it to water. Take acetic acid, C2H3O2. I'm sorry, let me write it down here a little bit. Sorry, give myself a little bit more room here, you guys. Sorry about this. All right, so you take acetic acid and you add it to water. So C2H3O2, and we talked about this already. You add it to water. Okay, what it will do then is that we saw then that the equilibrium, since it's a weak acid, it's going to favor the left-hand side of things. But what we see happening then is that hydrogen ion will form. Okay, and I'm sorry, the hydroxide ion. So let me put it as hydroxide for right now. H3O plus, and the acetate ion is going to form C2H3O2 minus. Okay, all right. And it's the formation of this here, the hydronium ion, that makes acetic acid an acid. Okay, so I'm sorry, this is not acetic acid. Sorry. This is sodium acetate. Sorry, this is sodium acetate. Okay, all right. So now that's what we see happening with acetic acid. Okay, so with sodium acetate, let's imagine what happens here. Sodium acetate, if you add sodium acetate into water, H3O2, it's going to dissolve in water. So let me go ahead and show you what happens. So it's going to dissolve in water, okay, and we're going to form then the sodium ions, okay, and the acetate ion. Okay, so what we're doing then is when we add this into the water, what we're going to have then floating around in the water then is going to be sodium ions, okay, and the acetate ions. Okay, so that's what's floating around in water. The hydration shells will form. But the question here is this: okay, will one of these ions do something to the water? Will it interact with the water? Okay, and so we already saw the sodium ion. And I'll write this down again. We already saw that the sodium ion, when it interacts with water, okay, the process by which it interacts with water does not happen, because then you form sodium hydroxide and the hydrogen ion. Okay, so we already saw, and I want to point this out to you, that does not happen. So therefore, sodium here, which is the conjugate acid of a strong base, sodium hydroxide, will not change the pH of the water. So the sodium ion itself, though, okay, so the sodium ion itself does not change, will not change the pH of water. Okay, all right, so that's the sodium ion. We know that's not going to happen. So the pH of water won't change because of this process here. But what about the acetate ion? Okay, let's see what happens if we do the same thing with the acetate ion. So we have then C2H3O2 minus. Okay, we're going to react that with water. Okay, and so let's see what happens in this case here. Okay, whoops, sorry, this here. Okay. All right, so if we take a look at what happens here, we form then when and so this is going to be then the conjugate base of a weak acid. We're going to form then acetic acid. Remember, water here is going to behave as an acid here, so it's going to donate hydrogen ion to acetate ion here. We form then C2H3O2 and hydroxide. Yep. So that's what we form when acetate is floating around in water. Okay. Now, looking back up here, we saw then that this base right here, when this forms right here, and we saw this, okay, when this base here forms, this is a very strong base. And so the equilibrium favors it shifting back and forming sodium ions and the hydroxide ions. So that's what we see there. Okay. If we take a look at this acid right here, and this is why I showed you this here, this then is going to be a very weak acid. Acetic acid is a weak acid. We already saw the Ka there is going to be very small. And so the equilibrium then is not going to shift back that much. So as soon as the acetate ion forms here, it's going to want to stay as acetate. So whenever, acetic acid. So whenever the acetate reacts with water, you're going to form then the acetic acid here. Okay, and you're going to form that and the hydroxide ion right here. You're going to form that, and you're going to form then the hydroxide ion. Okay. Now, because the equilibrium for acetate here, the acetic acid here, favors the left-hand side, whenever this forms, then the reaction, this process here, will not shift back to the left as much. There won't be as much of the acetic acid going back to the acetate ion and water. Okay. So that means then what you will have floating around in this water then, what you will have floating around in this water right now then will be sodium ions, some acetate ions. You're going to have obviously water floating around in there. Okay, so you're going to have water, but you will also have undissociated acetic acid. You'll have that floating around, and also the hydroxide ion floating around. And it's this right here that will change the pH of the solution. Okay, so when you have that hydroxide ion floating around, okay, and I want to point out to you again, and let me, I probably should clean this up a little bit. Okay, when you have that hydroxide ion floating around here, so we've identified then the major species floating around in the water here. Okay, so we have that it's this. Remember, that's considered a fairly strong base that will determine the pH of the acid, okay, of the water. Okay, so whenever you have this forming, then what will happen then is this here will increase the pH of the solution of the water, meaning then it will make the water basic. Okay. So by adding in a salt of acetate, so the sodium acetate here, when you add that in, sodium acetate itself is neither acidic nor basic. It has no pH. But when you add it to water, it is the interaction of the acetate ion here. It is this process right here. It's this process right here. Whoops, sorry. It's this process right here that does alter the pH of the water. Okay. So when you add a salt, okay, of acetate here, it will change. And so what do we notice then? Okay. So this can be derived from the acetic acid. Okay. So the conjugate base of a weak acid, okay, will make water basic. And that is what we notice about the whenever you have a conjugate base of a weak acid. Okay. Okay, so you end up with a basic solution. So you end up with a solution that is going to be basic, and that you got to make sure you keep in mind then why it's basic. It's this process right here. So you got to make sure you remember, or you focus in on this process right here. So this doesn't happen, but this process here, this does happen, and that's the reason why you have then a basic solution. You form a basic solution as a result of adding a conjugate base of a weak acid into water. Okay. All right. So the question then is, how can we calculate then if this equilibrium does occur? Okay. How then do we calculate the pH of the new solution? How do we calculate? We can measure it, okay, but how would we calculate for the pH of this solution here? And that's where I want to pick up with really quickly. Okay. So let's go ahead then. Let me let's do this here. We save this. We open up the whiteboard here. And let's talk about how we then can do that. Okay. So the question that I want to make sure you understand then is that if we have, okay, a solution, and let's that here. If we have a solution of acetate ion, okay, we enter H3O2 minus, okay, and we add that to water, okay, and we want to find then, whoops, sorry. Okay, and plus OH. Okay. It's the formation of this hydroxide ion right here that will determine the pH of the solution. So the question then is, how would we obtain then the concentration of that hydroxide ion right there? So we would set up our ice table, okay, and that's what we do. We'd set up our ice table. Okay, we would set it up, and then once we get the, and we would do the exact same thing that we did, and we'll work through a problem like this in just a moment. Okay, but once we get the concentration, the value for hydroxide here, we find the POH, subtract that from 14, and we have our pH. Okay? But the question then is, this is acetate. This is not, this is a conjugate, this is a base. Okay, so we need then a value for Kb for this particular reaction. Okay, so how then can we obtain Kb? How do we obtain the equilibrium constant for this process in order to solve then for the concentration of hydroxide ion? Okay, all right, so with that said then, let me go ahead and let's set up the law of mass action for this one here. So the law of mass action for this process then is going to be Kb is going to be equal to the hydroxide ion, concentration of hydroxide ions, times the concentration of the undissociated acid that formed C2H3O2, CH2H3O2, all over the concentration of the acetate of C. Sorry. And so it's going to be C2H3O2 minus. Okay. All right. So that's the law of mass action for this process, and I'm gonna hopefully you make sure you see that, because that's the law of mass action for this equilibrium here. Okay. All right. Now the acetate ion, we do know Ka. Ka is not for the acetate ion. Ka then is for this process here, C3O2. Okay, and for our purposes, I'm just going to go ahead then and plus C2H3O2. I'm going to leave out the water for right now. Okay. All right. So we know what the Ka is for this process. Okay. The Ka, I don't remember it off the top of my head, so sorry about that. But we do know this. We know what the Ka is. And actually, okay. So we know this Ka at 25 degrees Celsius. Let me try to find that for you really quickly. If I can recall, we had it a little bit further back, and I don't have my table with me. I think it was, if I remember right, which I don't trust my memory, but hold on one second. If I can find it, I will give it to you, you guys. Sorry about that. Okay, well, anyway, I think it was about one on the range of 1 times 10 to the minus 4, somewhere in that range. Okay. Again, don't quote me on that. I sorry, I don't have that in front of me here. But the point then is that we know this. This we don't know, but this is known. Okay, so at 25 degrees Celsius, we know this value. We can find it. Okay, and so what we want to do is we want to be able to use this in order to find this Kb here. So let me go ahead and set up the law of mass action for this process. And this is going to be hydrogen ions, okay, acetate ions, 2H3O2 minus, all over undissociated acid, HC2H3O2. You know, this bothers me. Let me go ahead. Let me try to let me go ahead and quickly look it up for you. And Ka for acidic acids. I don't want to use some arbitrary value. Ka for acidic acid. Yeah, I wasn't too far off. Acidic acid, there's 1 point, so I just looked it up. This is 1.8 times 10 to the minus 5. So 1.8, so it's about a little off. Okay, 1 times 10 to the minus 5. Okay, so we know this value. So the point then is that we know that value. Okay, all right. So with that said, then what can we do here? So I've given you the law of mass action for this process. And this is the law of mass action for this equilibrium here. Okay, let me go ahead then, and I'm going to go ahead. I'm going to do something really quickly here, and let's combine these together. Okay, let's combine these together. What I'm going to do then is, let's say we multiply Ka, multiply these two terms together, Ka times Kb. Okay. All right, so we multiply that together, then we're going to have then the concentration of hydroxide ions, concentration of the acetic acid, okay, all over concentration of the acetate, C2H3O2 minus. Okay, so that's going to be Kb, sorry. Okay. And Ka here then, let's multiply, write that in. That's going to be then hydrogen ion, concentration of hydrogen ion, times the concentration of the acetate, okay, all over the concentration of the acetic acid, C2H3O2. Okay. All right. Let's take a look at what happens here, you guys. Okay. So when you multiply this together, look what happens. This term cancels out. This term cancels out. Okay. And so look what we have left over. Look at what we have left over here. So when you cancel that out, then when you multiply Ka times Kb, you're going to get then the concentration of hydroxide times the concentration of the hydrogen ion. Okay? And what is this but Kw? Okay? Which we know. We know what Kw is. This process here is, when we have to remember, this is over water, okay, and that gives you Kw. So therefore, okay, examining this, we see then that whenever you have Ka and you multiply it by Kb, okay, you will have Kw. And this we can use to our advantage, guys. So if we know either the Ka or the Kb, we know what Kw is. Remember, Kw is a constant. It's the ion product constant of water, which so it's going to be 1 times 10 to the minus 14, which means then in order to find the Kb here, we know what Ka is. So in order to find the Kb up here, we would take the Ka for acetic acid and divide it by the Kw. So this is going to be 1 times 10 to the minus 14. Oops, sorry, 10 to the minus 14. Okay, and we'll divide it by 1 times 10 to the 1.8 times 10 to the minus 5. And let me put that into my calculator really quickly. And then we will get the Kb for this process right here, because this is always going to be true. So let me go ahead and 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. Okay. All right. So Kb for this process then is going to be 5.6 times 10 to the minus 10. And that is how we get Kb. And once we have Kb, we can go ahead and set up our ice table with the initial concentrations here for the acetate ions, and then we can solve for hydroxide. And from that, then we can obtain the pH for the solution. This is going to be important here, you guys. So make sure then that you remember this relationship, which is a fairly simple one, okay, for us to use. Okay? All right. Let me go ahead and save this here. All right. With that said, we can now, with what we have there, we can go ahead and let's get back here, okay? And we can use that to work out a problem. Okay, so but before we do, let me go ahead and let me summarize here for you. Okay, and so I already talked about this. Then these are going to be the major components with the undissociated acetic acid in there as well. Okay, whoops, sorry. And whenever you have a conjugate base, okay, for a weak acid, like I pointed out to you, you're going to form then a basic solution because of the formation of that hydroxide ion. Okay, all right. And so some examples here of salts salts which contain then conjugate bases of weak acids, sodium fluoride and potassium acetate here. Okay, so sodium fluoride would be from hydrofluoric acid. The acetate here is going to be from acetic acid, like I pointed out. So whenever you add the fluoride ions or the acetate ions into a solution, into water, you're going to make then a basic solution. Okay. All right. So then, in order to find the Kb for that process, then we can go ahead and use this equation, which I just showed you here, and then therefore then we can use that to solve then for the equilibrium. We can solve then for the pH of a particular process. Okay. All right, so let's go ahead and let's take an example. Look at example. Good. All right. So this is then the conjugate base of a weak acid. So fluoride ion is a conjugate base of a weak acid. Why? Because this fluoride ion, you can imagine then, if you had hydrofluoric acid, okay, then you would form the fluoride ion. Okay, the fluoride ion then is, and I'm only doing this to show you that fluoride is going to be the conjugate base of a weak acid. Okay, so here we are introducing sodium fluoride into water, and we're introducing the fluoride ion into water, not in the form of hydrofluoric acid, but in the form of sodium fluoride. So we're going to take a look at then what happens when we add the sodium fluoride into water. Okay, so with that said, then when you add the fluoride ions into the water, okay, what's going to happen, okay, is that you will form then the weak acid, HF, and the hydroxide ion. Okay, so that is the equilibrium that we're going to be looking at. So let's go ahead and write that down here. Okay, so with that said, then fluoride ion, water, heading to the left, a little bit to right, HF, and hydroxide. Okay, so we need that. We're going to set up the ice table in order to solve for that. Okay. All right. Initial concentration of the fluoride ion. Sodium fluoride is a completely soluble compound. Okay, so that means then with the concentration of the fluoride ion is going to be for them 0.3 molar. Okay, and so initially, then again, we don't have to worry about water. We're not going to have any of the hydrofluoric acid. We're not going to have any of the water, hydroxide. Okay, all right. So with that said, then Q is going to be less than K, so it's going to be plus X minus X plus X here. Okay, and so therefore then we're going to have 0.30 minus X, and X here. Okay, all right, so the law of mass action for this equilibrium then is going to be, remember, this is a base, so we need Kb for this reaction here. So we need Kb, that's going to be a basic solution here. So therefore, Kb, then it's going to be equal to concentration of HF times concentration of OH minus, all over concentration, whatever. That's pure water. We don't have to, we don't worry about that concentration of F minus at equilibrium. So at this point, then, what do we need? We need Kb. How do we obtain Kb? Well, we are given Ka for this process. So we have the Ka here. We're given Ka for this first process here. Okay, and so in order to find Kb, which is what we need here, we got to use this Ka. So 7.2 times 10 to the minus 4. Okay, so to find Kb, then remember, and that's why I pointed out to you, we got to find then take Ka, and we're going to divide it by Kw by Ka. Okay, so that's going to be 1 times 10 to the minus 14 over 7.2 times 10 to the minus 4, and therefore we get then Kb. And let me get this for you. 1.39 times 10 to the minus 11. Okay. So there is our value for Kb then. Okay, so now we have determined Kb. We can go ahead and we can solve for this problem. At this point then, I think everything else should be familiar to you, so I'll be able to get through this fairly quickly. Okay, so it's going to be 1.39 times 10 to the minus 11. It's going to be equal to x squared. So I'm going to go ahead and substitute all that in. Okay, over 0.30 minus x. Okay, 5% rule here, folks, will absolutely hold. 0.3 here, this is 10 to the minus 1. This is 10 to the minus 11. Okay, so you can do the check afterwards if you want to, but for absolutely the 5% rule is going to hold. So ignore the x down here. Okay, we can solve then for x. X I get then is going to be 2.04 times 10 to the minus 6. Okay, so that's going to be the concentration of the hydroxide ion. Okay. All right, and so again, and that's going to be the concentration of the hydroxide ion. You can go ahead and substitute that in, divide the initial concentration by this value by x here, and you're going to see then that the percentage is going to be well below. I think it's like 6.8 times 10 to the minus 4%. So it's a very, very small percentage. Okay. All right, so at this point then, we're not done. We want to find the pH. So let's go ahead then and find the POH for this solution. That's going to be the negative log of 2.04 times 10 to the minus 6. Okay, and then I get the POH here as being 5.69. Okay, and then finally for the pH then, which is what they want, we're going to take 14 and subtract the POH from that, and I end up with 8.31. Sorry guys, 8.31 as the final answer. 8.31 is the pH of that solution. Okay. All right, and so with that said, then I think the only part that's really new here, and I want to emphasize this here, the only part that's really new is we got to deal with this right here, this equilibrium right here, and trying to find the KB. Okay, and finding the KB, then we got to use then this simple formula that I derived for you. Okay, and once we have the KB, everything else is the same. Okay, everything else is pretty much the same. You set up the ice table, you're able to find then the hydroxide ion concentration in this case. And from that, then you can go ahead and find the POH. From that, you can find the pH. Okay. All right. Very good. Well, what time does fly? It seems like we just don't have that much time. So, what I'm going to do tomorrow, what we'll do tomorrow in class, then, is we're going to talk about the what happens when you add the conjugate acid of a weak base. What happens when you do that and you add it to water? How does that affect the pH of water? Okay. All right, very good, you guys. I'll hold off on assigning the homework for this until tomorrow, until we have a chance to talk about this a little bit more. Okay? So please stop by or please ask your questions tomorrow in class after you watch this video. But please make sure you do ask those. Okay. All right, very good, folks. I'll see you tomorrow in class.